So this is an explanation on the home wiring circuits, which is pretty much two voltages with three wires and a neutral going in between them. So this is what you have to start with to think about these, is that you have a balance situation. And what that means is you have, on either side of these, you have equal loading. So before even doing any math, you can tell if you have 540 watt lamps on this side and you have 540 watt lamps on this side, the current is simply going to go through and around. The neutral is actually, the current's going to be zero, which is ideal, and that's what you hope for. Because the whole point of this neutral isn't, under perfect conditions, it would carry no load. But the point of it is that maybe you turn this light off, and then now suddenly this is imbalanced. Now that neutral is going to carry the difference in those two loads. And when you do these problems, you kind of want to assume that this is the situation, but then you can figure out what exactly is going to happen with the neutral. So that's kind of the core concept in the beginning. So going over to this one, I drew one here where you have 120 volts, which is typical, and you have your two hots, and here you have, first thing you're always going to do is turn these into resistances if they're not, which is, you have these are pretty much the three main equations that you have. You can use this one if he gives for example, if he gives like a coffee machine or something and says this is the wattage, and it's rated at this voltage, you can use this equation to, transform it to this one, and then you can figure out what the resistance is based on that. But you always check the voltage based on what it's rated at. So, like that question on the test where you cut off the neutral, you wouldn't base it off 240 volts. You'd base it off whatever the equipment was rated at, usually. So once you figure that, you have to get these to be in a series loop. And for example, here you have parallel, so you have to solve that, which is just this equation, right? So 1 over 5 plus 1 over 10 is equal to 1 over R total. And this is really 2 over 10 because we have to add the fractions. And then you can take that whole thing out, turn that into 3 over 10. And if you flip this or you replace these, you'll have RT is equal to 10 divided by 3, which is equal to, let me do that. 10 3.33 ohms. So right away now we have these two canceled out into series. We can pretty much replace that with just a series resistor. And we can tell that this side actually has less resistance than this one, which before doing any math, you know that means this one's going to have more current running through it. So if you go, now you can just use the regular equations up here, the V equals IR. So the current's just going to be 120 divided by 3.33 for I1. And then I2 is just going to be 120 volts divided by 5 ohms. So once you figure that out, I have your currents, and you can label as if you like. 36 amps. 24 amps. Sorry, let me fix the lighting here. And now, like I said, going back to this, you always assume it's a perfect situation. That's just the easiest way in terms of the direction of the current, because that's kind of what you're trying to figure out at this point, is you assume it's going to go in this way, and then you assume this one is going to continue that way, and it's going to be perfect, and we're not going to have to use this. But of course, that's not going to happen, because clearly you can see that loads are different. So the neutral is always going to carry the difference. So the difference, the I neutral, is going to carry. And this goes back to this point, because this is the node, right? And the whole, I think it's Kirchhoff's, that's the one that says, I entering is equal to I exit. that looks terrible. So pretty much you have 36 minus 24 amps is equal to, and now we know that this one is carrying 12 amps. And, to pick the direction, you have 36 going in, 24 coming out. So it wouldn't really make sense to put more in if you already have more going in than out. So you're going to take away 12 amps to balance the circuit. But now, even if, let's pretend you messed this one up. You said 24 amps was going this way. And you do this equation, you're going to realize that it wouldn't really make sense for it to go that way because you're adding them now when you want to try and aim for balance, right? So it wouldn't make sense to add them. So then, of course, you just flip the sign, and that would get you closer to having a balanced circuit, which is closer to 0. And then your neutral will again take the difference. So one other difficulty he might add to this question is if he says the lines are lossy or have resistance. He might say, hey, each one of these wires has a certain resistance going through it. And you got to figure out what's the drop going through. And drop, when you're looking through the circuit, you have to go along and say, is it dropping or is it actually, or what's happening to voltage through each spot? And it depends which direction you're going because current always goes from high potential voltage to low. It's kind of like this drawing over here. If current is always the direction is from high potential to low, and so if you go to here, if you check the voltage here is going to be at its highest. This is max, right? And here it's going to be the lowest. So if you're wondering, hey, this thing's going here to here, where's the voltage higher? Here or maybe here? And you think, well, if current wants to go to the lower area, and then this must be actually the higher voltage. And then from here to here, for example, if you're checking this side and this side, it's the same thing. Current's going from there to there. So this side probably has higher voltage, which makes sense because you're closer to the voltage source, right? Current's always going away and over and to 0 potential energy by the time it gets over here, right? And that's that.